Greetings to everybody. In this video I'm going to be talking about a common mode noise. It's a third part of the common mode noise series, third video should I say, except in this video we're going to be talking common mode noise in power supplies. Okay, we're going to be talking about what is the basically common noise. What is a common mode noise, problems caused by common mode noise, measuring common mode noise, and solving common mode noise. How do we solve it? Because the common mode noise, sometimes you cannot really reduce or kill altogether. But the aim is, according to the established protocols and standards, this is caused by some of the problems with the common mode noise. Now, the established protocol is basically there's a load line, okay, and if any signal goes over the load line, even if it's just one spike, it can create a havoc. So the idea is, and usually the most common mode noise is generated anywhere between 0 and 30 megahertz. And that's what I have got, from 0 to 30 megahertz measurement, which was captured from the instrument. Now, the idea is not to try which I don't think one would be able to, but nonetheless, the idea is to remove any signal above and bring it down below the actual red load line from 0 to 30 megahertz. And that's what I have done by using different filtering techniques and different ways of suppressing common mode noise and differential noise, of course, and so on. And I have managed to bring all the signal way below. You can see it over here. Where is the 0 line, reference line. In that way, that power supply is not going to be a troublesome for any electronic device to interfere with, and also it's not going to be detrimental for the health. Okay, on that note, let's go back to common mode noise filters. A bit of an explanation. Okay, as I explained, in the electromagnetic interference, EMI, okay, one can it can actually broadly be divided into two different types: conducted emission and, of course, radiated emission. And of course, we're going to be talking conducted emission and, of course, a bit of a suppression of the actual radiated emission. Among this conducted emission can be further classified into two types, differential and basically common mode noise. And of course, today we're talking about the common mode noise in power supplies. So basically, why does switch mode power supplies or power supplies generate common mode noise? The effect is caused by the rapid change of voltage changes basically at switching nodes, components, and different parts that form the power supply in the actual circuit. And they're actually pushing and pumping the current through the wiring and through the circuitry, which now starts to actually create magnetic fields and basically creates common mode noise interference. Common noise, common mode noise in power supplies is called that way because the direction of the noise current of the positive and the negative, okay, side of the power supply have basically same direction. If you look at it, same direction. They go that way, they go that way. And now, due to the capacitive coupling of the positive and negative with different sort of elements of the circuit, they actually form the actual differential voltage between the reference ground and the positive and reference ground and negative. And that's what actually is what the actual common noise is tapat in. Now, problems caused by common noise can severely interfere with any electronic device by making it basically inoperable. Can also be detrimental to one's health. Measuring common mode noise, basically if you look at it over there, you can use a scope, you can use an oscilloscope, you can use a spectrum analyzer, or you can actually use a very sensitive current clamp meters, which will give you a fair idea of the magnitude present of the actual common mode noise. Now, how do we solve it? Now, solving common mode noise problems basically you apply different sort of common mode chokes, filters, ferrites, and of course there are many ways and other specialized sort of techniques of applying proper layout and of course shielding of the circuitry and wiring. Alright, enough of theory. Now let's go back basically what we're going to do now. In order to demonstrate, I've got basically a small little switch mode, step-up power supply from basically 0 to 5 volt input via these two crocodile clamps, which will be connected to my 5 volt power supply, which comes from that box over there. Then, of course, I've got scope probes connected into the spectrum analyzer, where I'm going to be actually measuring. And you can see that's my basically reference 0, and here is 1 0 marker, and with the second marker I'll be measuring the magnitude of the actual interfering signal, the actual common mode noise. And of course, using the spectrum analyzers and the scopes are beyond many people because they quite pricey. Not quite pricey, very, very, very pricey. And they're beyond many sort of people having access to this type of a sort of equipment. But nonetheless, that's why I started making a small little instrument, and I call it Batos Common Mode Noise Filter, tester, which is very, very reasonably priced for what it can actually do and measure, with a special test probe, okay, which actually just gets clamped onto my positive wire going into the power supply. And it will pick up the actual common mode noise and display it on the actual instrument, the magnitude. And then once we start, of course, then I got the filter over here, which I'm going to use to sort of try to filter the actual noise. That's just one of the filters. As I said, I'm not going to use different types. I'll just use this specific one. And you will actually see that we actually reduce. Besides on the spectrum analyzer, you'll also see it on the little instrument that we make, that yes, noise has been reduced. And of course, by positioning also like a different ferrite beads, where it's a toroids, for clamping on the wires and things like that, like over here. You can't just clamp it anywhere. And also, you can actually see by how much, by using, whether it's a filter or whether it's a toroid or whether it's a clamping sort of ferrites, by how much more or less numerically you have actually reduced it. And are you sort of making progress in a right direction, let's put it that way. Now with the common mode noise filters, you can never really, as I said, kill it 100%, but the idea is to eliminate these spikes or the actual noise above the red line to just below the red line type of thing. And luckily with this particular filter that I have captured the measurement of, I have managed to actually reduce it substantially, type of thing. So it depends how much customer is prepared to pay for the filter and things like that. On that note, let's start again. I've got a dummy load connected, which is 10 ohm, on the output of the actual 5 volt power supply, and I'm gonna basically connect it up. And of course, here is my radio, and I'm gonna switch it on just now. First, let me connect it up to a negative. Okay, negative, and then you will see. Let me just switch it on. Okay, there we go. Now you can see power supply is on. Okay, now let me just null. Okay, I have already nulled it. Okay, all right. Now it's showing. If you look at it, the instrument is showing full scale 50. Now I'm gonna disconnect just to show you. Okay, I'm just gonna disconnect the power supply quickly, and then you see it. Okay, now it's off. Now it's on. The sensor is picking up the actual noise coming from the actual filter, and it getting picked up by the sensor into the instrument. So instead of instead of using the spectrum analyzer, which is, as I said, beyond many people, but let me show you on the spectrum analyzer. If you look at it from my reference point, of course, the spectrum analyzer, I got it 100. The center line basically represents 100 megahertz. And now why? The noise is basically from 0, so it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I'm basically measuring, it's 20 megahertz per division. So it's basically, I'm measuring from 0 to about, you could call it 160 megahertz right now. Which close to 2, it's 8 times 20, that would be 1, 2, 3, 4, sorry. No, that would be, sorry man, oh, it's too cold, yeah. Okay, so it's 5 times 20, that's 100, and 100, that's basically, I'm measuring from 0 to 200, I'm confusing myself. All right, so we got basically a very broad, if you remember right at the beginning of the video, where I actually said, you get the harmonics of the actual, from basically 0 DC to whatever, many times harmonics of the actual interfering signals that actually generate noise. So I got a very broad spectrum, and I can actually see by how much I actually reduce. But of course, that is on the spectrum analyzer, which is too expensive. Yet over here, very simple measurement. Anybody can interpret. You don't need to be RF engineer or whatever, technical person or anything like that. You can actually see the reduction of the noise. Now, if I disconnect, let me show you. If I disconnect, the signal disappears. Okay, the common noise, because the power supply is off. Now, watch now when I switch on, the power supply comes on. Okay, you can see it. Okay, it's on, and here is the noise. And the noise that I'm picking up is basically 26.4 dB. I have already put a marker over there, and you can actually see it over there. So it's from here to there, it's 26.4 dB, which is quite a substantial, and I've got it even down here. Now what I'm going to do is, I'm going to basically disconnect, and I'm going to try and connect a filter. Now let me do it this way. All right, and what I do is I put the positive to positive, okay, negative to negative, that's the output of the filter. Sorry, that's the input of the filter, should I say. And, okay, this is the, okay. Now let's just connect it up over there. Let me just clamp it. All right, now the filter is getting basically supplied via the filter. Still the same setup, except right now, first goes through the filter into the, and the power goes into the switch mode power supply into the same dummy load. Now, if you look at it, first of all, you can actually see substantial amount. Now, I'm just going to move that marker. Watch this marker over there, okay? I'm going to move it more or less to the center of the actual, the signal. So let's look at it. Okay, where am I now? All right, it's somewhere around there. All right, it's plus minus. Okay, right now I have brought it basically from the maximum, which was minus 26, I have brought it down close to my 0 reference line. From here to there, it's actually minus 4 dB. The actual still noise present. Okay, so if we say 26 minus 4 gives us minus 4 dB. That gives us about 22.4 dB attenuation of the actual signal, which is quite good. And that should solve most of the problems and bring the actual noise below the actual reference line, which, as I said, authorities have come up with as a guidelines for any sort of interference and problems. Now, let's try, okay, I'm just going to switch off the power supply, okay. Now, let's try
persons with disability, that's
and switch on.
In the presidency, Dr.
Okay, let's switch on direct.
Zuma, indicating some time back that she's not planning to come back. So your suggestions, please pick a candidate for us
direct.
on 072 702 1702 and 011.
Okay, now my radio is on. Now my radio is on.
The JSC is up today by 430 points.
And you
so
can
far.
hear it, it's
No
actually very
major
clean.
upward movers, but
Now I'm going to
Richmond
connect
and
it up direct.
Goldfield, both of them now a couple of days in a
Okay,
row.
no
Sassel
filter.
and implants, all of them up by around
Listen to it.
2.5%.
The sound will
The rand is
disappear.
slipping a little bit, down 6 cents against
Okay.
the dollar. Currently at 8 rand.
You can actually see. It's totally disappeared. The actual voice. You just hear it basically white noise. And that is the actual signal radiated and also with these wires and whatever without the filter. And it's flowing through the wires, and because it's connected to the power supply, radiates all over the show. And of course, my antenna on the radio picks it up, and it just blanks out the sound. Now, if you look at it over here, basically it's full. Over here, basically it's full signal. Let me put it softer, and you can actually hear it. You know that it actually blanks out the radio. So I'm going to switch off. Okay. Now there's nothing connected. Okay, now I'm just going to put it softer. And now again I'm going to put the filter again. And watch how much it actually, okay, let's do it this way. Negative goes to negative, positive goes to positive. Same here on the filter. Let's just do it. Very difficult with one hand, but nonetheless I'm trying my best. All right. Now, first in, first. Now it's going through the filter. Okay? It's going through the actual filter into the filter that we make. Okay? Okay, this is just a ground wire, but nonetheless, okay. Through the actual filter. Now, let's look at it over here. Let me just do this. Okay, now it's connected. Okay, now you can actually see, okay, from 50, it has gone to about 20 something, 28 or so. Let me just do this. Okay. All right. And let's listen to the radio.
The sound of chewing. So
Now
the tune's
it
okay
is.
for me. It doesn't really get
Now
the
you
blood
can
boiling,
actually
but
see it over here
after
again.
you've tuned,
It has brought the
and now you
signal
want to
right
clean
down
your
here.
teeth, and you go.
Okay.
Stop.
So
Don't-
you can
don't
actually
do
see
that.
that the filter has actually filtered the common mode noise.
Someone in this room does
And
it
at
from
least,
time to time.
at
No
least,
names
let me
mentioned.
put it softer, you can at least sort of enjoy your radio. And by bringing these spikes down, you have actually basically eliminated the radiation of the wires and made the signal substantially weaker than what actually is tapped in. And if you look at it, basically, let's switch it on again. You can hear it. You can see it over there, and you can see it over there.
He's chewing the guy who was
So from basically, yeah, 50, I just positioned the sensor
Okay.
properly, okay.
Alright, so
There we
now
go.
eating. What's that now?
It's actually
Oh, still
22 plus minus. If you look at it, 22, 20, yeah, 22, somewhere around there. From 50 to 22. And that was good enough to actually, let me put the radio off again, and that was good enough to actually kill all the noise. And I have done it with the aid, and I can confirm that I have actually, without using the spectrum expensive equipment, I can see where I'm going in the right direction. Now, by adding extra sort of ferrites and twisting the wire like a twisted pear type of thing, I will further reduce, and you will actually see it on the instrument. It will go even more down. By introducing more powerful filter than this, you will see it actually even on this little instrument that we make without using any expensive equipment. Yes, you are going, you're decreasing the signal, the interfering signal, should I say, the interfering signal that gets radiated from this switch mode power supply. So yeah, basically I have demonstrated the little common mode noise tester that we make. And the beautiful thing about this common mode tester is, let me just get another sort of sensor. Just by changing the actual different sort of probe, I can use it for coaxial cables to measure common mode in antenna systems, or by plugging, let me just do it this way, by plugging, I'm plugging in another sensor, I can actually measure the common mode noise in power supplies and wiring. Yeah, so on that note, basically I've just sort of did a demo on the actual common mode noise tester that we make, and of course the instrument is available at Batos. Of course, it will help you if you do pick up sub noise even on audio cables, wherever you got the noise problems, you can actually try and use the instrument and see whether you're solving the problem, whether you're fitting the filters at the appropriate, like even on this particular antenna. You can actually see now this and this sort of clip-on ferrites are placed at specific positions. And why at specific positions? Because the instrument told me so. I could actually see by moving the ferrite up and down where is the biggest attenuation that I'm actually obtaining. So on that note, thank you for watching Batos common mode noise in power supplies, and this is a part 3. Thank you.